The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
So we're going to begin today's lecture by actually looking or examining a reaction that is central to the reactivity of this class of organic compounds, and the name of this reaction is nucleophilic acyl substitution. So like I said, this is a reaction that we did tackle before when we looked at organic acids, and we're just going to revisit it here. So in this reaction, nucleophilic acyl substitution, the first thing that happens is that you will have an attack of the acyl carbon by a nucleophile. Okay, so direct your attention to the bottom of the screen right here. We have a nucleophile that I'm highlighting, attacking what is essentially the carbon of the acyl group. So I'm talking about this carbon right here. And what actually ends up happening is that it adds to that carbonyl compound, resulting in the formation of a tetrahedral intermediate that looks something like that. I'm highlighting it in parentheses right now. So what happens to complete this reaction is a basic elimination step. So this tetrahedral intermediate that we have right here will then collapse with the expulsion of the weaker base. Okay, so that is basically what happens in a nucleophilic acyl substitution. So in the first step, you'll have nucleophilic attack. This is a nucleophilic attack step we're talking about right here. That's the nucleophilic addition step. That results in the formation of our tetrahedral intermediate right here, which then collapses to form our acyl compound, our product, and the leaving group. Now remember, when this tetrahedral intermediate collapses, the carbonyl group is restored. So a pair of electrons on that oxygen right here will come down to restore or reform the double bond between the carbon and the oxygen. And while that happens, simultaneously, this leaving group right here will exit with this pair of electrons right there. So the electrons used to form that bond will leave with the leaving group. Okay, so that's pretty much nucleophilic acyl substitution in a nutshell. Now, I am also going to remind you of the reactivity order of this class of organic compounds. Okay, so which is the most reactive, which is the least reactive, and why? Now, the reactivity order of nucleophilic acid derivatives is basically determined by the nature of the substituent that is bound to the acyl group. Remember what the acyl group is? That is our acyl group right here. So whatever is bound to that position right here, the carbon of the acyl group, is pretty much what determines the reactivity order of these substituents. So I'm going to explain that in more detail. So when you have substituents like halogens, for instance, chlorine or oxygen, or any substituent that is of significant electronegativity, what will happen is that it will pull or withdraw electron density away from the acyl group, the acyl carbon, towards itself, because it's more electronegative than this carbon right here. So in the case of an acyl halide, a chlorine atom is much more electronegative than a carbon atom, so it will pull or draw electron density away from this acyl group. Same thing in an acid anhydride, and the same is true going down the group, but obviously that effect will significantly diminish because, as you can see, moving down that group, the strength of those substituents, or the electronegativity strength of those substituents, is progressively decreasing. So what happens in this case is that if you're pulling electron density away from the acyl carbon, you are effectively making it more electrophilic. You're making it more electron loving. Remember that the carbonyl group right here of the acyl group is a polar group. So the oxygen will carry what is a partial negative charge because of its electronegativity, and there will be a partial positive charge at the carbon. Now what happens when you introduce another electron withdrawing substituent at this position right here? You further withdraw or remove electron density from this carbon right here, which makes it even more electrophilic, more prone to nucleophilic attack, more susceptible to nucleophilic attack. So the higher the electronegativity of the substituent, the higher the electrophilicity of the acyl group, and the more prone it will be to nucleophilic attack. So it will participate in nucleophilic substitution reactions at a much faster rate. So with that information in mind, it should be very easy for you to predict that acyl halides will be the most reactive acid derivatives, because of the simple fact that halogens in general are the most electronegative groups. And you can expect amides to be the least reactive acid derivatives, because of the simple fact that that amino group right there is not very electron withdrawing. So that's pretty much what is, or the underlying chemistry behind the reactivity of this class of compounds. But before we move on to the next slide, I'll mention one more thing. You have to remember that the stability of the substituent is also important. Because remember, in a substitution reaction, that chlorine atom right there will have to exit if it is a leaving group. That entire group right there in an anhydride would have to exit. That this group right here, that thiol group, would have to exit. That alkoxy group in the ester would have to exit. So the stability of that substituent as a leaving group is also important. And as you know, the stability of the leaving group is related to its basicity. So that's another factor that you should take into account. So all in all, what we've gone over in this slide is the nucleophilic acyl substitution reaction, as you can see, which is basically a two-step process: a nucleophilic addition or attack, followed by an elimination process. And as far as the reactivity order of this class of organic compounds is concerned, the most important thing that you have to remember is the simple fact that the nature of the substituent, or the substituent bonded to the acyl group, will in large determine the reactivity of that compound. So we're going to move on